Okay, let's start from thermal conductivity detector. Yeah, detector is quite a long, old one. Okay, but still, it's working. And then there is a case. There are cases for this detector only is used. Okay, and as name indicates, note this detection is based on thermal conductivity difference. Okay, most common in the past, simple, universal, and responding to all lights. This is not sensitive enough to detect light emitted from open tubular column, right? So this thermal conductivity detector TCD is not often used for the open tubular column. Okay, let's look at first this one. This detector structure. This is quite simple actually. There is two electrodes, and then here you put this kind of hot filament, usually made of platinum. Okay, and here the uh, eluent is introduced from here, and then it passes this part. Okay, it sweeps this part, and then this eluent comes out from this part. Okay, and this is maintained at high temperature, and this filament conductivity, okay, depends on the eluent composition. Okay, but same here. Okay, here this one, no, this is a low volume internal thermal conductivity detector. Okay, uh, yeah, they almost identical. And now this carrier gas now carries your light. Okay, let's assume that. Let's imagine now carrier gas flows through this detector, and it comes out. Okay, and then you measure the this thermal conductivity of this filament. Okay, and you will get some number. Okay, for when the carrier gas flows here, and then when carrier gas now carries contains light. Okay, and light, when light part passes through this hot filament, and this since the thermal conductivity of the gas is different from your carrier gas, and then this filament conductivity changes, although little. Okay, and then you amplify this filament uh, conductivity. Okay, and then it can be converted to the chromatogram. All right. And here this table shows the thermal conductivity for different gases. Okay, and hydrogen gas thermal conductivity is 0.17, and the unit is rather peculiar, and like that. Okay, here when light emerges from column, gas conductivity decreases, then filament get hotter, resistance of filament metal increases. Okay, depending on the solute, this filament, not the resistance changes. Okay, and then you take that the difference. Okay, the voltage across the filament changes, since actual operation is done by passing the very precisely controlled current through this filament. Okay, and the resistance value of this filament changes when solute pass through this filament, and then uh, the voltage uh, between these two ends of the filament is different. Current is constant, but the resistance value of this hot filament changes. So voltage drop changes. Okay. Yeah. So measure the voltage change. So sensitivity of TCD is inversely proportional to flow rate. Okay. So if you increase the flow rate, yeah, the sensitivity decreases. Okay, so linear range is order of 5. Okay? Hydrogen and helium give lowest detection limit. Okay, why? The hydrogen and the helium thermal conductivity is very high. Okay, so you can detect a small amount of one light when they are carried away with hydrogen gas or helium gas. Okay, but usually hydrogen gas is not used. Okay, but helium gas is good, but this helium is quite expensive one. Okay, very expensive. So this is not economical. So people use nitrogen gas. Well, in my lab, my own lab, I have gas chromatograph, and it is installed with this the TCD. Okay, and I usually use argon gas. Sensitivity increases with increasing filament current. Of course, it is actually proportional to the third power of current. Right? Yeah, we can I can derive that the sensitivity, but not here. Okay, its sensitivity also increases with the decreasing flow rate. Okay, detector block temperature. Yeah, this one. This block temperature higher the better. Okay. And another, I think this is the most widely used detector for GC, which is the flame ionization detector. By the way, this thermal conductivity detector now you solute separated solute now pass through this detector part, and still here from this outlet you can collect separated your solute, right? This is not a destructive detector. Okay, but with the flame ionization detector, this is a destructive detection method. Okay, let's look at this figure. Now this gas flow from here. Okay, and then you also input this hydrogen gas from this part, and then here this is a hydrogen flame. Okay, this is air in red, and this is the hydrogen flame, and this carrier gas now flow from this column. This is column end, and then it contains solutes. And here, when it passes through this flame, and the solutes now what? All evaporate, all destroyed. Okay, and since it is a negative electrode and this is positive electrode, and the solutes are the ionized, and it attracted to this collector. And you can here look at that. This solute now ionized to become positive ion. Yeah, and then it is collected here to this positive. Let me see. Uh, this one is a negative electrode. Anyway, so you measure the current. Okay, and this is really sensitive, much more sensitive than thermal conductivity detector. Okay, only about 1 in 10 to 5 uh, the atoms produces an ion. Okay, carbon atoms produces an ion. Ion production proportional to the number of carbons in flame without an halide. Yeah? 10 to minus 14 ampere between flame tip and collector. The flame tip and collector, you measure the current, but with an halide. Yeah? Since an halide is ionized, so the current is increased to 10 to minus 12 ampere, yeah? 1 picoampere. Wow, very small current, but it is no problem to detect this amount of current. Okay, it is converted to voltage, amplified, and then read out the signal. Okay? Response of a flame ionization detector is proportional to the mass of an light. Detection limit of this detector is 100 times smaller than TCD, much more sensitive. Respond to most hydrocarbons. Okay, most hydrocarbons are ionized by this hot flame, okay, hot hydrogen flame. But these uh, gases cannot be detected by this detector. Hydrogen gas, of course, because you use hydrogen, this gas as a fuel to this one flame, and neon, nitrogen, oxygen, uh, monoxide, carbon dioxide, water, and ammonia, nitrogen dioxide, monoxide, hydrogen sulfide, silicon fluoride. Yeah, those compound are not the FID are not sensitive to these compound. Okay, so N2 gives the best detection limit. Uh, I mean, this carrier gas signal is proportional to the number of carbon atoms. Its linear range is in the order of 7. Okay? And another type of detector is electron capture detector. Wow, this is very sensitive, but this is I haven't seen this detector. Not This is not universal in comparison to FID and TCD. This is sensitive to halogen containing molecules, carbonyls, this is nitriles, and this nitro groups, okay, organometals. Nearly insensitive to hydrocarbons, alcohols, and this is what ketones, okay. Carrier gas is usually nitrogen or 5% methane in air, elute ionized by high energy electron emitted by beta emitter from foil containing radioactive nickel, the mass number 63. Wow, this is use nickel isotope here. This is isotope source, and here this is eluent in, and it contains what, your solute, okay. And then this cell body is cathode, negative potential applied, and this anode is positive potential applied. And here, while your solute pass through this area, since it contains this nitrogen isotope, it emits electron. It is beta electron, right? It undergoes beta what radioactive decay, and the beta electron now hit your solute, and it is ionized. Okay, electrons in the plasma are attracted to an anode, producing small current. Okay, now ions hit ionized species now hit this anode. As a result, small currents are produced. Okay, and then you can detect the small currents. When analyzed with a high electron affinity enter the detector, they capture electrons and um, decrease the conductivity of the plasma. Okay, they capture electrons here. That's why this detector is called electron capture detector, ECD. The detector responds by varying the frequency of voltage pulses to maintain constant current. The frequency of the pulses is detector signal. Okay? ECD is extremely sensitive, comparable to mass spectrometry. Okay, this is very sensitive, but this is not widely used, and this part is very expensive. Okay, let's temporarily stop here.